All right, I'll get started here. I'll begin with a word of prayer. So, Heavenly Father, we thank you for this day. I thank you for these students. Just ask that you just bless this class, help us to understand a little bit more about math together, and just help the students to ask good questions as they have them. Lord, in your name I pray, Lord Jesus. Amen. Amen. So we are into we're covering rational expressions today. And so what's a rational expression? So basically, in a nutshell, it's essentially something of the form like a polynomial over a polynomial, something like that. And then sums and differences of these things, all right? So it's basically like fractions of polynomials. That's a rational expression. So a rational function, what's a rational function? A rational function has the form f of x equals to p of x over q of x, where p of x and q of x are both polynomials. All right? So essentially what we're looking at today is how to manipulate the formulas for rational functions. So the first, goodness gracious, the first order of business here is to ask the question, well, what's the domain of these functions, right? Yes, Michael?
The domain is any number that is not equal to 0.
That's about right. Yeah, the domain of this function, right, is going to be x such that q of x is not equal to 0, right? In other words, the domain is the set of inputs which don't give you division by 0. So let's look at some specific examples, like example 1. Suppose we're looking at, f of x.
Let me finish writing this down.
Well, you can do that. 1 over x plus 4. All right? The question is, what's the domain of this rational function? Yes, Michael?
The domain is x is not equal to 4.
So you say all x not equal to 4, right? Mm-hmm. Now, if I was to write that in interval notation, what would it look like? You're like, most of you probably are like, let's just not do that, right? But we're going to keep doing that. So all x not equal to 4 in interval notation, this would look like minus infinity to 4 unioned with 4 to infinity. See, that would be the domain of this expression 1 over x plus 4, okay? So sometimes it's pretty easy to figure out, right? Like you just kind of look at it, see it. Let's try another one. Example 2. What if I had f of x equals to 1 over x minus 3 plus 3x plus 2 divided by x squared minus 3x plus 2. What would the domain of this expression be? So here what we want to do, yes, Michael?
So we need to factor out the second.
Factor out the second one. I think that's a good idea. Let's see here. So 3x plus 2. Can you guys factor that? Just the denominator?
Oh.
How do we factor x squared minus 3x plus 2? Excuse me. x minus 1, x minus 2. Yep, x minus 1, x minus 2. All right, now Michael had a good idea to factor it. Now that you look at this, what are the three numbers that we cannot permit in the formula for f of x? Yeah, Michael?
1 and 2.
1, 2, and 3, right? X not equal to 1, 2, 3 describes domain of f. So the domain of this rational expression is everything except for 1, 2, and 3. Now, can you guys write that domain in interval notation? Let me do it. Here's how it goes. You have minus infinity to 1, unioned with 1 to 2, unioned with 2 to 3, unioned with 3 to infinity. So there you go. That would be the domain of the rational expression here. Sorry I'm writing it too low. I know you guys can't see past the heads of the others.
Let me take a photo.
Take a photo is a great idea, yes. Let me get out of the way. No one wants me in the photo. All right, let's see. So, I'm not going to belabor these, but this is the first kind of question, right? Where is a rational expression defined? Answer, where the denominator or denominators are non-zero. Okay? We good? All right. So, next up, we're going to look at how to simplify rational expressions. And there's a lot of things to talk about here. So we'll start with the most basic part, all right? So something like example 3. We might be up against 8x squared plus 16x divided by 4x squared. Now, the instructions, this is number 21 from the book on section R7. It says write each rational expression in lowest terms. So we're supposed to write this in lowest terms. What would that mean? That's just fancy talk for let's simplify it, right? Let's try to simplify it if we can, and we can. So, so here's how that goes. We have 8x squared over 4x squared plus 16x over 4x squared. All right? Now, some things cancel out here, right? Like the first fraction, we get what? Yeah, we get the x squareds cancel, and 8 over 4 is 2, right? And the next one simplifies to 4 over x. 16 over 4 is 4. X over x squared is 1 over x.
4 over x squared.
Yep.
Why did the x's cancel when you add them like that?
Why did the x's cancel?
8x squared over 4x squared, when you write that as 2, why is x squared not written as 2?
Because if we have x to the power m over x to the power n, that is going to simplify to x to the m minus n. All right, so like, and generically speaking, if I have a, b over cd, we can look at that as a over c times b over d. So if we have a product, if we have a fraction of products, we can look at it as the product of fractions. I'm using that idea when I go from 8x squared over 4x squared to 8 over 4 times x squared over x squared.
Yep.
And that's why I got 2 times 1, which is 2. All right? So there's that one.
So
Yep.
x squared divided by x squared is 1.
Right. That is correct. Example 4, we might be up against something like x squared minus 4x plus 4 divided by x squared plus x minus 6. Actually, I don't like that. Just a second. Let me fix it. Let me make that a 3 upstairs, make it more interesting. And we're supposed to try to reduce that if we can. All right? I'm not sure if we can or can't. But to be sure that you can't cancel something out, what should we do? What's the thing that most of us need to practice more on?
Factoring.
Factoring, yes, very true. So this here is what? So x squared minus 4x plus 3, I think we can do x minus 1 and x minus 3 there. And downstairs, we can do x plus 3 and x minus 2, I believe. All right? So in some sense, this fraction is already in lowest terms. Like I cannot further reduce it. So that's it. So oh, okay.
Unless you could do x plus 2, x minus 3.
Well, but it is what it is. Oh, I mean, well, we could switch the orders of the factors is true, but that's pretty much it. So example 5, on the other hand, something interesting will happen. If we have x squared minus 4x plus 4, like I erased because I'm a dummy, how would that go? Well, the denominator is the same as the one we just had, right? So we can still factor that as x plus 3 times x minus 2. But how do you factor the numerator here? How do you factor x squared minus 4x plus 4?
X minus 2, x minus 2.
X minus 2, x minus 2. I think we have a winner. Yeah. 2 people said that, so it must be true, right?
So we cross off the like terms out.
Cross the like terms out. So you're saying I can cancel this and that, right?
Yes.
And that leaves me with x minus 2 over x.
Or x plus 3.
Right. And there you go. That's the fraction in lowest form. All right? Does that make sense? When is that step? When is this true? When is this true? This is true if x is not equal to 2. Technically speaking, that simplification has a string attached to it. Like, this is only valid for x not equal to 2. When x is equal to 2, you have 0 over 0, which is technically undefined. So this will be important for those of you who go on to calculus, for example. Yeah.
Oh, and x is not equal to negative 3 also.
That is true. X is not equal to minus 3 as well. That's right. So the domain of the original expression is x not equal to minus 3 and x not equal to 2. So we could always be talking about the domain in every one of these examples, but after the first couple, we just stop talking about domain because it just gets boring to keep talking about domain for every problem. Yep.
So for example 4, the domain would be like those
Oh.
numbers?
So for example 4, it's the denominator that's the troublemaker. So here the domain would be everything except for like minus 3 and 2. It's the same as example 5 actually, because they have the same denominator. The domain is completely governed by the denominator. The numerator doesn't matter. All right, so next up here, we're supposed to multiply or divide as indicated. So let me put up a couple here, let you guys chew on them, see if you can do them. Example 6 will be 15 p cubed divided by 9 p squared multiplied by 12p divided by 10 p cubed. So that would be example 6. Example 7 will be y cubed plus y squared divided by 7 multiplied by 49 divided by y to the power 4 plus y cubed. All right. So our goal is to multiply and simplify in each one of these examples, okay? So while I'm moving the camera, you guys see if you can work it out. 49, yeah. So how do you manipulate fractions? Like, how do you multiply fractions, guys? Do you know? Yeah, we just multiply the numerators and multiply the denominators, right? Like, the rule of algebra that we keep using is this. Let me just write it kind of symbolically up here. If we have A over B, right, times C over D, how do we do that? Well, we just do A times C over B times D. That's how that goes, right? So I use that method here. But if I'm smart, what would I do before I multiplied, actually? So I probably would simplify before I multiplied, right? So what, if I can, what's 15 over 9?
5 over 3.
So this is 5p over 3. Why is it p? Why not p squared? Why not p cubed over p squared? What is p cubed over p squared? It's p. P cubed over p squared is p. How about 12?
3 minus 2.
Right. And what's p over p cubed?
P squared.
1 over p squared, right? So this is 6 over 5 p squared is how that simplifies. Because 12 over 10 simplifies to 6 over 5, right? And p over p cubed is 1 over p squared. All right? Now let's multiply. Or, I mean, actually, I don't need to, let me be smarter. Let's not multiply. Let's do what?
So can
Yeah, can we cancel when they're in different fractions like that? We can, because they're multiplied, right? So, like, this is an allowed step of algebra. I can cancel this 5 with that 5 like that. All right? And what is p over p squared?
1 over p.
Yeah, just 1 over p. So we have 6 over 3p. Can we simplify that?
2 over p.
What?
Yes.
2 over p.
2p.
Right, 2 over p. And there you have it. There is another way we could have done this problem. Another way you could do this is just multiply everything on the top, multiply everything on the bottom, and just do it all at once. All right? Should I show you that? Would that be helpful?
Sure.
All right, so let's try the other way. So I did it in steps this time. Here's to do it not so much in steps, but just directly. 15p cubed divided by 9p squared times 12p divided by 10p cubed. All right, so I just multiply the numbers. 15 times 12 is 140, 145? I don't know.
180.
180? Oh, thanks. So apparently 180. P cubed times p? P to the 4th. Downstairs we've got 90. And p to the 5th which is 2 over p.
Dang, that's some crazy easy simplification.
Part of the reason this seems easier is it's the second example I've done using these steps. They're actually kind of similar. This is more how I tend to calculate. But the steps we were making were good steps in the other way.
Just trying to restate my focus.
So let me bring example 7, and I'm going to refocus it over here. We've got example 7 was y, you guys have to read it out for me, y cubed plus y squared divided by 7 times what?
49 over y4 plus y cubed.
All right. So let's try to simplify that. Now I strongly advise you not to multiply this one out like we did at the end of the last example, right? If you distribute the numbers out and just like multiply it out, it probably will not help you. It probably will hurt you. When you have things like this, you need to look for like common factors to cancel. We need to look for common factors to cancel. Can we? How about there's something easier than that? I mean, that's not wrong. You guys are not wrong. Maybe. I can't see it. Wait till I get back to the board. I really need glasses. I was looking for something easier. How about this? See the 49 and the 7? That's just give me a what? 49 out of 7? 7. So we could just put that out front. All right. Now this, I can factor what out of this? I can factor y squared out of that. All right. And how about this? I can factor, now you guys told me to factor y cubed out of that. I agree. That gives me y cubed times y plus 1. A lot of you are probably having trouble tracking me because you're like, I graded the test, right? So you're not solid on factoring yet. Very shaky. This needs to you got to fix that. And it can be fixed. The good news is the stuff we're doing, guess what? It's all factoring. It's like just always factoring, right? So even if you just go on with the course and just do the sections that are in front of you, like work all the problems in section R7, if you actually work through them, it forces you to factor in order to understand, right? So you can't avoid it. And you notice something else? These factoring problems are easier than the ones I was focusing a lot of my energy on because you don't need to complete the square, do you? These are just pull stuff out, see it, right? That's because this is R7. It's one of the review sections. Technically, this is like from the prerequisite course. But there's not a clear dividing line between college algebra and intermediate algebra. Really, there's about 30% overlap in these courses. So listen, guys, most of people who take college algebra, one of the major things you're trying to learn this semester is factoring. So like if you're not solid on factoring yet, it's okay. There's still time to fix it, right? There's still time. But you do need to fix it. Y plus 1 and y plus, hey, we could cancel that, right?
Yeah. Oh.
See that?
Yippee.
So these are like that. Check this out. If I've got a 2 upstairs and a 3 downstairs, that just simplifies to what?
Oh, y over
Yeah.
7 over y.
7 over y. And there you have it.
Oh.
Can you explain that jump from y squared over y cubed to 7y?
So we've got 7y squared over y cubed. We can write that as 7 over y cubed minus 2, if you like to look at it that way.
That does help a lot. Okay.
Like there are 2 different sort of simplification rules I go with, guys. I wrote one of them on the board here a bit ago, which was that x to the m over x to the n is x to the m minus n, right? But there's another way to look at that, which is x to the, let me say a, over x to the b. We can also write that as 1 over x to the b minus a. So these are 2 kind of handy-dandy patterns to keep in your head to quickly simplify powers. When you have quotients of powers, this is how to simplify. Of course, it depends on what you're after, right? All right, let's look at another one here.
So let me take one picture. Oh,
You already got a picture of this, Michael. You're fine. Don't worry.
let me.
You took a picture of that like a while ago. All right, so let me put up the problem, and then I'll let you guys chew on it for a second while I move the camera. I'm on example 8. So we're starting to get into the ones that are a little bit trickier. Here's one. We might be up against something like x squared plus 2x minus 15 over x squared plus 11x plus 30 times x squared plus 2x minus 24 divided by x squared minus 8x plus 15. See if you guys can do that one. So I think we need to factor everything, right? Look at this, four factoring problems all at once. It's fun, right? Let's see here. So what's x squared plus, see, let's do it here. So the first one is x plus 5 times x minus 3. This guy right here is x plus 8x, wait a minute, no, x plus 6x, x plus 6 times x minus 4, I believe. Then, what we got here? This one, well, 30 is 5 times 6, so that's x plus 5 times x plus 6, all right? Last but not least, we've got this one here, which to me looks like an x minus 3, x minus 5. All right? Does anything cancel out?
Yes.
Yes, the
Plus 5 can.
x minus 3s, x plus 6.
Everything but the far right, basically.
Oh, and the x plus 5s, yeah. So, wow, look at that. X minus 4 over x minus 5. Hooray! That's kind of surprising, isn't it? Does this look like that? Does this look like x minus 4 over x? It does not, right? Yeah. So, example 9. Here we're up against 7x plus 8 over 3x plus 2 minus x plus 4 over 3x plus 2. Well, that's kind of, this one's too easy. This one's too easy. Why is this too easy?
Just cancel the entire denominator.
Well, we can't just cancel the denominator. But the point is, Excuse me, guys. So here's the deal. If you have a plus b over c, guess what? It's a over c plus b over c. But notice that in order to go one way or the other, we have to have what? Same denominator. And the nice thing about this problem is it happens to have the same denominator. So here we go. Now it's not, there's still opportunity for making a mistake here, right? Because we could forget to distribute the minus. So we have to distribute that minus. How's that go? 7x plus 8 minus x minus 4 divided by 3x plus 2, which is 6x plus 4 over 3x plus 2. I take it back. I'm starting to warm to this example. That is 3 times, wait a minute, excuse me, that's 2. See, that's a 2 times 3x plus 2, isn't it? See, I can factor a 2 out of the numerator. And if you do that, do you see what we could cancel, Michael?
3x plus 2.
3x plus 2. Yep. Which leaves us with 2. So this is 2. That doesn't look like 2, does it? But it is. Except when x is what? What's the fine print here? X not equal to minus 2 over 3. See, if x was minus 2 over 3, this calculation is nonsense. Because then we'd have division by 0 in that context. All right.
How did you get negative 2 over 3, Professor?
I set the denominator equal to 0, Michael.
Well, I thought you got 2.
Well, yes. My point is that that calculation is only legit.
True if x is not.
Only legit if x is not equal to that. So the domain of this expression is all x except for x equal to minus 2/3. Well, guys, what's 1/3 plus 1/5? 1/3 plus 1/5, go. Nobody?
Eight 15.
8/15, is Michael right?
Yes.
Yes, he's right. So, a reminder, 1/3 plus 1/5, how do we do that?
Oh,
5,
the least common multiple.
right? 5 over 15 plus 3 over 15, right? So what I was doing is really doing what? I was doing 1/3 times 5 over 5 plus 1/5 times 3 over 3. That's how we add fractions. At least that's one way. So I've got 5 plus 3 over 15, right? Which is 8/15, as you guys told me a second ago. This idea we still need when we're working with expressions. All right? Now, so for instance, example 10, I might be up against, I don't know, 3x over x squared plus x minus 12 minus x over x squared minus 16. Sorry, this example is a little bit difficult to start with. My apologies. It's not the most simple example I could have picked. Unfortunately, your book has kind of a gulf between. It doesn't have the easy examples I want to give you guys right now.
So are they too easy?
I should just make one up, right? Let's hit pause on example 10. Let me give you example 11.
No, I got this.
All right. I will accept my fate then. Let's see here, 3x. This is x plus 4.
x
minus 3. And this one is what?
x plus 4.
X plus 4 times x minus 4, right? So a smart way to do this calculation would be to notice that we have a common factor here, right? Do you guys see it?
Oh,
See that?
x plus 4.
So let me rewrite this. We can write this as 1 over x plus 4 times 3x over x minus 3, right? And this can also be written as 1 over x plus 4 times x over x minus 4. So in view of that, we can factor out 1 over x plus 4 times times what's left here. Does that make sense? No? I see some knowing. You're still working on it? I was about to look for my phone, but that would be dumb because I left it with my son.
So we use the common x plus 4, distribute it out to both fraction form, and then I don't get to jump to the next step.
See,
It's just factoring out 1 over x plus 4.
yeah, since it's both places, I can use the distributive property.
That makes sense then.
So the generic pattern I'm using, guys, is if I have like 1 over like AB plus 1 over AC, I can rewrite that as like 1 over A times 1 over B plus 1 over C. This is a simple algebra pattern to look for. Yeah. When I was learning algebra in college, I used to love learning new patterns. And then there came a time when there were no new patterns to learn, and then that was sad. But you guys still have patterns to learn. It's a happy place, right? No.
So if the factors are the same, leave it as 1 over the same factor.
Right. Now, are we done? We're not done. So, can we make this into one fraction? We'd like to do that, yeah? So, what do I do here? So, I will multiply this by x minus 4 over x minus 4. And then I will take this x over x minus 4 and multiply it by what? X minus 3 over x minus 3. See, if I do that, that's the analog of multiplying the fraction by 5 over 5 or 3 over 3. See, I'm multiplying it by 1 to make the denominators match up. Why am I allowed to do this? Because I'm just multiplying by 1, right? So why do I do that? So that now the denominators match, and I can do what? I can add the fractions. So I've got 3x times x minus 4 minus x times x minus 3, all divided by
Hold on.
x minus
I can't
3.
see.
I'll get out of the way in a second, Michael. I put it in the budget for like active camouflage, teaching wear, but so far the light bending shirt is not coming to stock. I didn't think I was going to make a reference to Predator today, but it happened. All right, so can we do better? Well, now I just heard x minus 3 and x minus 4 on the top and the bottom, but I cannot cancel them because it's not everywhere. So what I want to do here is multiply out, see if I can make anything prettier. So 1 over x plus 4, we've got ourselves a 3x squared minus 12x minus x squared plus 3x divided by x minus 3 times x minus 4, which works out to 1 over x plus 4 times what would you got here? You got a 2x squared minus what? Minus 9x, I think. Can we factor that? We can factor the thing in the numerator now, right? What do you have? That's x times what? I've got an x times 2x minus 9 divided by x plus 4 times x minus 3 times x minus 4. At this point, there's nothing more we can do. Game over.
What a long step.
That is a long problem, isn't it? Yeah.
Time for another photo.
Excuse me. All right, guys, there's another kind of problem that we should look at here before we're done. So the other thing that sometimes happens is you have what are called complex fractions. I don't like calling them complex fractions. I like to call it a compound fraction. A fraction of fractions. What do you do with a fraction of fractions? So let's talk about that. So a fraction of fractions, example 11, you might be up against something like x plus 1 over x plus 2 divided by x minus 1 over x plus 2. So this is a fraction of fractions. What do you do to a fraction of fractions? How do you make this look simpler? I'm going to write it again over here so I can do something to it, okay? What should we multiply this by?
X.
X is a good idea.
Distribute x to all terms.
But instead of, how about, almost the right idea, Michael, but instead of x, we should multiply by x plus 1. Multiply by 1 is correct, but the one we're going to multiply by is x plus 2. I'll do it like this. X plus 2 and x plus 2. I can do that because I'm multiplying I'm multiplying the denominator and the numerator by the same quantity. That doesn't change the expression, right?
Oh, so it distributes the denominator.
Yeah, if we multiply by x plus 2, we're going to clear out the fraction. See, what we get is x times x plus 2 plus 1 divided by x times x plus 2 minus 1. See, because the x plus 2 over x plus 2 cancels. Does that make sense? And then what? Maybe something nice happens here. Let's see, x squared plus 2x plus 1, x squared
Least common denominator.
plus 2x minus, well, it's denominated already. Is that a word? Denominator? Can we factor anything here? X squared plus 2x plus 1, does it factor?
Yes.
It does? Okay, cool. How does that factor? X equals what? X plus 1 squared divided by, how about x squared plus 2x minus 1? Does that factor? It does, but not nicely. So in this section in the book, it would just stay like this, you know. Let me tell you how that factors. X squared plus 2x minus 1 is x plus 1 squared minus 1 minus 1, which is x plus 1 squared minus 2, which is x plus 1 plus the square root of 2 times x plus 1 minus the square root of 2. And as a matter of common math custom here in this course, we don't do that kind of factoring here. We'll just leave it like this.
Don't forget to put I.
Oh, there's no I here, because it was in minus. This one's not prime. It's not prime, but we just leave it like that. You could factor it like that if you wanted to, but we don't. So that's a pretty good sampling of the rational expression section. If you guys got questions on it, this is basically the first problem in your mission 2. And with that, I will hand back your test. So, yep.
Do you know where the printers are on floor 3?
The what? Printers. I know nothing of printers.